Hello everyone. So in the last lecture we have seen the etching and doping techniques. So in the etching process we have discussed that there are two different types of etching process. One is wet etching, another one is dry etching, and we have seen there are some limitations for wet etching, and also there are some limitations in dry etching as well. However, they have their own advantages. For example, in case of dry etching, you'll be able to create an highly anisotropic structure. However, in case of wet etching, it's usually isotropic. Very difficult to create a highly anisotropic structure. But again, dry etching, in case of dry etching, the equipment is very complex. Batch process is not something that one can make. In case of dry etching, it's very difficult to create a batch process. However, wet etching is relatively simpler, and you can go for a batch process as well. Then we also have discussed doping techniques, and we have seen in doping also we have two different types. One is thermal diffusion, another one is ion implantation. So in case of thermal diffusion, we have seen the profile is something like this, where the concentration near the surface is much higher. So mostly all the dopant atoms concentrate or stays near the surface of the semiconductor material or any material for that matter. In case of ion implantation, the concentration is high or highest somewhere below the surface at certain depth. It's not on the surface, it's somewhere below the surface, because high velocity atoms are interacting or hitting the surface of the semiconductor. So obviously that atom will penetrate the surface a bit and then will get settled. So that's why you'll find that the concentration is highest at certain depth. Now today we will also check what are the imaging techniques available in order to characterize different devices. So we already have discussed what are the characterization processes involved in microfabrication or sensor fabrication or device fabrication, and imaging technique is one of the most important one. Why it is most important? Because most of the device or sensor require certain sort of geometry. Now once you start fabricating those geometry, you need to visualize or you need to check whether that geometry has achieved or not. You achieved that geometry or not. For example, if you take a substrate and if you want the electrode to be of certain shape, say of this shape, then you'll use mask, you'll use deposition technique, etching, lithography, whatever it is, and then probably you'll get certain electrodes on top of a substrate. But after fabrication, once you fabricate that, you need to check whether the electrodes are of this shape or not, whether you could achieve this shape or not. This may happen that during the process, due to certain fault in the process or due to certain issues in the process, the shape is not fully developed, something like this. This part has not been developed due to certain process. Maybe the mask was not properly aligned, the deposition was not sufficient, the mask window was not sufficient, something happened and you could not achieve that. So to confirm that, okay, whatever I wanted, I got this shape of electrode or any other, say, active material, then you need to image that device and then figure out whether it is okay or not. Most of the structures that we develop in device and sensors are in the range of micrometers or less. That's why we are unable to see those structures properly with a naked eye. That's why we need to take help of different microscopy techniques. So the first choice is an optical microscope, because optical microscope is relatively I would say affordable, and then the operation of an optical microscope is also relatively easier. So it's not very complicated equipment as such. I have given the working principle of the optical microscope over here, but you already have studied these things previously in different optics course or maybe in your school days. So just to give you the structure, or just to remind you the structure of an optical microscope, I have given a schematic image over here. So it has an eyepiece, then it has objective lenses. So this is where the objective lens is kept, and then you have a stage where you put the material or the device that you want to characterize, and then you can focus this object just by changing the distance between the objective lens and the object. So you need to figure out what should be the distance between the object and objective, so that the image is focused and you get a clear picture. So you can move this stage up and down in order to focus that. And nowadays you also will find there is camera arrangement kept somewhere here. So that camera will take picture of the image that is received by these lens, and then there is a computer where you can see the image of your device or electrode, whatever it is, right? So this is a typical arrangement of a microscope, an optical microscope. So it also has coarse focus and fine focus. If you rotate this, the stage will move up and down, and then there is a switch. This switch is specifically for the light arrangement. So you'll find that there is a light source also somewhere here, and then this light source will help us to visualize the entire thing, right? And in certain cases light sources are at the bottom. So it depends on whether your microscope is upright or it's inverted, right? So these details to some extent you already know. Now one of the advantages of optical microscope is it's simple and user friendly. It's not very complicated. Okay, anyone can directly go to an optical microscope. Maybe it's a matter of minutes if he or she has never used it. Then it will take a few minutes to learn, maybe an hour to learn how to use an optical microscope. So it's simple and user friendly, and the sample preparation is also fairly easy. So what you have to do is, if you have a device, you just put the device with the substrate beneath this objective lens, and then you use the focus knobs in order to focus the image, and you will get the image. And this is a multi-purpose equipment. Multi-purpose, why we are calling it multi-purpose? It's not only for device characterization. Even in biology also you will find use of the optical microscope for visualizing viruses, bacteria, cell, tissues. In biochemistry you will find a use. In metallurgy also you will find a use. Almost in most of the science areas you will find the use of a optical microscope. And in device fabrication though, we need an optical microscope quite often, especially when you make a pattern. You, for the sake of confirmation, you take that, put under microscope and see whether the pattern is made or not. If the pattern dimension is very small, optical microscope is not the best thing to use, because optical microscope has a limitation as far as the feature size is concerned. If the feature size is something less than 1 micrometer, it's very difficult to work with an optical microscope. So one of the major problem that you may find is, if the feature size is less than 1 micron, then the working distance, that is the distance between the objective lens and the object, that is this distance, this has to be very small. So it will almost touch the substrate. Sometimes it's not very easy to focus the feature. So in that case, it's not recommended that you go to an optical microscope and then characterize, and then it's also very difficult to work with and very less working distance at higher objectives. So these objectives, you will find there are multiple objectives in an optical microscope. This can be 10x, this can be 100x, 20x, so on and so forth. Okay, so you can rotate this nose piece, and then you can put the required objective on top of your sample. If you want to use an 100x microscope, that is the magnification, 100x is the magnification. If you want to use higher magnification, that is 100x, you just rotate and put the 100x objective on top of your image. That is the way we actually use an optical microscope. However, as I have said, if your feature size is very less, then optical microscope is not sufficient to visualize or to check whether the pattern is correct or not. In device fabrication and sensor fabrication, oftentimes you will find that the feature sizes are less than 1 micron. They are probably in nanometers, 100 nanometers, or sometimes less than 100 nanometers, say 50 nanometers, 10 nanometers. Then optical system is not a good choice, because optical system has a limitation of say 400 nanometer or so, because the wavelength of a visual light, the minimum wavelength that you get for a visual light is visible light is around 400 nanometer or so. You can't go below that. That's a theoretical limitation. However, in practice, achieving 1 micron or less than 1 micron, say 800, 700 nanometer itself is a challenge. Okay, that's why in that case we take help of an electron microscope. But before we go to an electron microscope, let us see what is the resolution of an optical microscope. So the equation is given over here. The resolution delta x can be calculated with this equation. 0.61 into lambda is the wavelength divided by numerical aperture. Numerical aperture is n sin theta. So these details probably you already have studied in optics or courses related to optical microscope. I am not going in details of that, but there are certain differences that I have said between optical microscopy and electron microscopy. So one of the major difference is, in case of optical microscope, the energy of photon is around 2 electron volts. In optical microscope, we use visible light. Now energy of photon in visible light is around 2 electron volts. However, in case of energy in electron beam, or energy of an electron beam, is around 10 kilo electron volts. So it's quite high. So the energy of electron beam is significantly high compared to the energy of photon in visible light. Then wavelength of visible light is around 600 nanometer. Around say 400 nanometer is the lowest possible visible light, maybe blue. If you consider ultraviolet, then it will go below that, but ultraviolet anyways is not visible, it doesn't come under visible light. So wavelength of a visible light on an average is like around 600 nanometer. However, wavelength of electron beam is 0.012 nanometer. So it's in angstrom. Then numerical aperture of optical microscope is around 1.2. However, the numerical aperture of electron microscope is quite less, significantly less. It's 0.01. Then resolution for optical microscope, it's 300 nanometer. That is probably the theoretical limit. In practice, if you go below 1 micrometer, you'll start finding it difficult. You'll start that imaging becomes difficult. However, resolution for electron microscope is few nanometer, and sometimes it's in angstrom. You also can image different crystal planes if you using an electron microscope. So the resolution is quite high. That is, very small feature size also can be imaged using a electron microscope. So here is the basic details regarding electron microscope. So in an electron microscope, you will find that there is an electron gun present, And there are majorly two different types of electron microscope. One is scanning electron microscope, another one is transmission electron microscope. So scanning electron microscope is well known as SEM. This is the acronym of scanning electron microscope. However, transmission electron microscope is known as TEM, right? So in case of scanning electron microscope, you have an electron gun, then there is an electron beam that falls on top of the sample, and then there is a backscattered or secondary electron detector that detects the reflected electrons, and from that reflected electron one can image the surface of the sample. However, in case of transmission electron microscope, again you have an electron gun. This electron gun will produce an electron beam. It will go through a sample, so it's like a transmission process. It's a reflection, however it's a transmission. So it will go through the sample and then it will fall on a fluorescent plate where you will find the shadow of the sample. From the shadow you will be able to see whether, or you will able to figure out what is the dimension of that particular sample. So it's like, if I give you an analogy with an optical system, it's like you have a torch, you light the torch, and then if you put the hand underneath the torch, you'll see the shadow on the floor. So from the shadow you will be able to understand what is the feature size, right, or what is the shape of that feature. So this is what a transmission electron microscope does. In this case, in order to create the shadow, because it's an electron beam, what people use is a fluorescent plate where you can get the shadow of that sample. Now here I have given a comparison between scanning electron microscope and TEM. So in case of scanning electron microscope, the acceleration voltage is between 1 to 40 kilo electron volt. Usually we use 5 kV or similar energy or voltage, and in case of TEM it varies between 1 and 1000 kilo electron volt. The magnification in ACM is 200 kx, and in case of TEM it's 2000 kx, so it's almost an order higher. Then the resolution of a ACM is few nanometer. However, in TEM you will find the resolution is few angstrom. Basically you can see crystal planes using transmission electron microscope. The imaging method is based on scattered electron beam. In case of TEM, it's like transmitted electron beam. So these are the basic difference between ACM and TEM. Now briefly we will see what is the working principle. So this is an image of a ACM, scanning electron microscope. So you can see that system is not very simple. You usually connect this with a computer where you will find the images. So this is the schematic image of a scanning electron microscope. So you have an electron gun, it goes through an anode which partially focuses this electron beam, and then it goes through condenser lenses. There are 2 condenser lenses which further focus this electron beam, and then it passes through an objective lens. This objective lens has a control of XY scan. Then it falls to a sample through a backscattered electron detector. So there is a kind of passage that allows this electron beam to go through it and fall on top of a substrate, and then this backscattered electron detector detects the backscattered electrons that is reflecting out from the sample, and then you have a secondary electron detector that also detects the electrons coming out or electrons reflecting back from the sample. And then in many cases you also have a X-ray detector present. This X-ray detector is used to characterize the material. So this is the simple schematic that shows how a scanning electron microscope works. So once you have a substrate, say it has certain feature, so this electron beam will fall on top of that substrate, and then the electrons will start scattering from it, and these detectors will then detect those electrons and then image the morphology of that particular sample. In fact, in most of the cases the system also comes with an EDS, so it also detects the reflected X-ray and then can give you the material present on the sample, the details regarding the material present on the sample, right. So this is the system, how it looks like. Here is the electron gun, this is the sample holder. So you have a vacuum chamber here, you take out this sample holder, place your sample on top of the sample holder, and then you put this sample holder inside this chamber and vacuum it. So this is again a kind of vacuum chamber present over here, and then you start your imaging. You switch on the electron gun and you can start your imaging, you will get the image on a PC. Now sample preparation is also a very important aspect of imaging technique. In case of optical microscopy, sample preparation is quite simple. However, in this case what you have to do is you have to say make a 1 by 1 substrate, 1 cm by 1 centimeter substrate, and then you have to attach your sample. If it's a thin film, either you deposit the thin film on top of it or you attach the sample on top of this glass slide with an carbon tape, double-sided carbon tape. It's a carbon tape which has adhesive in both the sides. So you put the carbon tape on top of the sample holder, and then the adhesive is also present on top of this carbon tape, you put the sample on it. Okay. So then you can insert the sample inside this vacuum chamber. The 1 centimeter by 1 centimeter is a kind of representative figure. It can be 2 centimeter by 2 centimeter, but it can't be very large. It depends on the sample holder also. Sometimes the sample holder allows, for example, it's like a disk, it allows say 5-6 different samples, and there are sample holders which only allows one sample on top of it, right. So advantage of this kind of sample holder is you can load 6 different samples, put the holder inside and then vacuum it. Then once your characterization of one sample is done, you rotate this holder and then the next sample will go underneath this electron gun and you can image it without breaking the vacuum. So it saves a lot of time, right. So in most of the cases people use this type of sample holders only. So this is scanning electron microscope. And why we use carbon tape? Because if your sample is a non-conductive sample, and in certain cases if semiconducting sample, what happens is because electrons are coming and hitting the surface, you'll find a lot of charge accumulation on top of the surface. Now if the charge accumulation is high, then you will not get a clear image. The image will be blurry because the new set of electrons that are coming and hitting the surface of the sample the surface is already populated with electrons. So new set of electrons will hit the other electrons only. So it's very important that whatever charge is accumulating on top of the surface is also going out of the surface. For that purpose, conductive carbon tape is used, and this conductive carbon tape ensures if there is a charge, it goes through the carbon tape and goes out of this sample surface. If your sample is not conductive, then if you go for an scanning electron microscopy, the operator will ask whether you need a gold coating or not. So usually what they do is they first coat a very thin layer of gold on top of this sample so that the charge accumulation problem is not there. Charge accumulation will lead to a blurry image which is of no use. Okay. So this is the sample preparation and why we use carbon tape, what is charge accumulation and why it creates an issue. This is the details related to that. Similarly, but one thing is clear, in this case sample preparation is not as straightforward as we have seen in case of optical microscopy. In case of electron microscopy, this is a typical image of an electron microscope where you have a electron gun on top. Then it goes through again anode, condenser lenses, objective lenses, intermediate lens, this is projector lens, and then it falls on a fluorescent screen, and that is where you can keep your sample. Okay. So once it goes through the sample, it will create a kind of shadow on this fluorescent screen. It's simple, as I have said. If you have a torchlight, put your hand, you'll get the shadow underneath. It's similar thing, but we use condenser lens and objective lens in order to focus that, okay, in order to focus the beam on a right place. Now this is the electron gun. Here is where you put your sample, and then somewhere, this is the side view, somewhere here you'll see there is an fluorescent screen, okay. So in that case, the feature size that you see here, it's visible, the shadow is visible with a naked eye, okay, and then the same thing will also be visible in a PC connected to it, okay. So this is how you characterize samples in transmission electron microscope, but the sample preparation in this case is bit more complicated. So usually what people use is a TEM grid. A grid looks like this, which is made of copper or nickel, and it has mesh like this, as you can see over here, and then there is a transparent carbon film beneath this mesh. So you will find TEM grid with different mesh size, and then you will find TEM grid with transparent carbon layer beneath, without transparent carbon layer. Now if you want to characterize say nanoparticles, you should use a TEM grid having a transparent carbon layer beneath, because the usual process is you take this TEM grid, you drop cast your sample on top of it, and you dry it out. Now if there is no transparent carbon layer beneath, then the nanoparticles will go through this mesh and you will find no sample is there. However, if you are characterizing say nanofibers of high aspect ratio, then even if you don't have a transparent carbon layer, they will stick to the grid, because the aspect ratio is big, so it will stick between the mesh. So if this is one mesh, so that fibers will stick in that layer, because the dimension is higher than the mesh dimension, right? So that is how you decide what TEM grid we should use. And then once you dry this TEM grid, you put this TEM grid in the sample holder. So sample holder will have a, so sample holder is like a rod like thing. On top there is a place where you can put the TEM grid, and then you put the entire sample holder inside the TEM. Just you insert it, and then you lock it, and then you start the vacuum process. So once the vacuum process is done, you switch on the electron gun and start your imaging. This is the usual process. You will find transmission electron microscope with EDS as well, similar to what you have seen in scanning electron microscope, and then you can also do elemental studies. What are the materials present on that particular sample? You can study that as well. Usually these equipments require liquid nitrogen, because the electron beam is of high energy, so there is a lot of heat that it generates. That's why we need liquid nitrogen. So you usually find that there is a liquid nitrogen chamber, maybe on that side of that image you'll find it. You fill this with liquid nitrogen, and then you start your analysis. This is the usual process. So from the device image only, you will be able to, you can understand that the process is not as simple. It's a bit complex process. It takes time, and it's not very easy. Typically one can use these kind of facilities once they are properly trained. It's not like optical microscopy. Training requires months, 1 to 2 months of time, depending upon how much time you invest on that particular training process. But you can understand that the process is not simple. Okay, so this is transmission electron microscope. Now there are 3 take-home messages. The first one is there are different types of microscopies. This can be electron, this can be optical, and this can be force microscopy as well. So force microscopy is a separate type of microscopy. We have seen optical and electron microscopy in this lecture. Then electron microscopy has higher resolution compared to optical. You already have seen. In case of electron microscopy, you can go till angstrom level. But in case of optical microscopy, the resolution is around 1 micrometer. Theoretically, you can reach up to say 300 nanometer or so, but in practice, you will find going below 1 micrometer itself is a challenge. And then different electron microscopes are available based on the transmission and reflection. So we have seen one is scanning electron microscope and another one is transmission electron microscope. So in the upcoming discussion, we'll see what is force microscopy, and we also will check what are the other material characterization techniques for the sake of completion. Till then, thank you.